Hey everybody. So I'm going to do another Taylor series, or actually in this case, I'm going to do a degree 5 Taylor polynomial to start. So let's jump right in. We're going to do the degree 5 Taylor polynomial for one of our trig functions for sine of x. Okay, so we're going to find, let's say t. This is the notation I used last time, the 5th degree Taylor polynomial for f of x equals sine of x at 0, centered at 0, okay? So let's first remember what this means. The 5th degree Taylor polynomial is the polynomial, it'll look like this, at 0, right? So it's just the first up to the 5th degree term for our Taylor series, right? So it's a finite version of the Taylor series, right? And it's what we often use when we use these things, right? You know, one of the big cases I keep making for why we're even doing this is that these are handy things to have around when you need to do work with a function that's difficult to deal with at times, right? Trig functions can be tricky sometimes. Especially in combinations with other things, but once you introduce them as polynomials, a lot of things can become simpler, especially if you're doing, you know, physics or engineering or chemistry, and you can live with an approximation. Then you often see that going out to 5 terms or maybe 10 terms, which isn't that many either, is a very, very valid approximation, meaning it's a very nearly identical up to a high degree of accuracy. So we build them exactly the same way, right? There's nothing, these coefficients are still given by the nth derivative at a divided by n factorial, okay? So that hasn't changed, we just stop at a certain n as opposed to the Taylor series. So I find them the same way. I'm gonna go ahead and compute a bunch of derivatives of f of x. So f of x equals sine of x. F prime of x is cosine of x. The second derivative is going to be negative sine of x. Third derivative is going to be negative cosine of x. The fourth derivative is going to be back to sine of x. And I would usually stop there. It seems like we've well established a pattern, but we're only going up to the 5th degree. Let's just compute all 5 derivatives. We get cosine of x. Okay. Then let's just evaluate each of these at x equals 0. I'm a lot less concerned with finding a pattern right now, since I'm only doing these 6 terms. It's just as easy to compute each one explicitly as it might be to go about trying to identify the pattern that's happening. So f of 0, sine of 0 is 0. F prime of 0, that's the cosine of 0, is 1. F double prime of 0 is 0 again. The third derivative at 0 is going to be negative 1. The fourth derivative at 0 is going to be 0 again. And the 5th derivative at 0 is back to 1. Okay? So this is pretty straightforward so far. Right? Using this formula, I get that C naught is equal to the derivative, the 0th derivative of the function at 0 over n factorial, but the numerator is just going to be this, right? These are going to be my numerators with n factorials in the bottom. So this one's going to be 0. C1 is going to be 1, right? 1 over 1 factorial. C2 is going to be 0. C3 is going to be negative 1 over 3 factorial. C4 is going to be 0. And C5 is going to be 1 over 5 factorial, right? All I've done, put the 0th 1 over 0 factorial but the first one over 1 factorial, second one over 2 factorial, third one over 3 factorial, right? Just following the program of that, that formula that we developed a little while back, okay? And so right now, I'm already ready to write down this 5th degree polynomial. C0 was 0, C1 is 1, so I have 1x. I have 0 for C2, so there's no x squareds, and then I've got minus 1 over 3 factorial, that's the coefficient of x cubed, so this is x cubed over 3 factorial. I don't have a C4 term, or I do at 0, so that's gone. And then I get an x to the 5th times C5, there's C5, so I get x to the 5th over 5 factorial, okay? So there's our 5th degree polynomial approximating sine. Okay. Let's jump for a moment to the graph and take a look at this approximation. There you are. All right, so there's the green, it's our sine. And so here we've got the function just equal to 0, so it hits our graph right here, it matches it perfectly there. If I go up to the first term, remember the first term of our Taylor polynomial, let me actually write it out really quick here. Let's do, sorry, there it is. So we had x minus x cubed. Sorry, I don't have my tablet nearby at the moment, and I'm writing with a mouse, which is not very good. So that's a 3 factorial plus x to the 5th over 5 factorial. All right. So this is our approximation to sine. Oh, that's terrible, but we're going to leave it. All right. Sine of x is approximately x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So what we're looking at here is just this first. This would be the 1st degree Taylor polynomial, just x, right? And you probably have heard about the sine x is approximately x near 0, right? And that's what shows up right here. They look very similar near 0, right? Or you probably learned at some point that the limit as x approaches 0 of sine x over x is 1 because they're so closely aligned there. All right, let's add some terms. So now I'm going to a cubic approximation. So now we don't have the 5th degree term yet, but we've got the cubic, and we can see what happens from going from the first term where it matches for a little while but then shoots off. It's bent back to match it quite a bit longer, right? That area where they lay right on top of each other, or at least appear to, has extended a little bit further. And it also stays closer, even when it's bending away. It's still not as bad as the approximation with the linear function as it looked. Then let's go one more. We'll add our degree 5, and we see now we've bent around quite a bit more, okay? So this approximation is looking a little bit better. However, notice I've got this series, I'm adding similar terms. We'll talk about what those are in a minute, and it does appear to be getting better and better as we go. So let's go back to our paper and investigate a little more. This series, okay? We stopped after 5 terms, okay? So let me come to a new piece of paper. We've got f of x equals sine of x, and we just discovered that sine of x is approximately equal to its 5th degree Taylor polynomial, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Okay, that's where we had gotten to. Notice when we built this thing, right? This pattern is going to continue, right? We got a derivative of cosine, which puts us back here. Then the next one's going to be negative sine, then negative cosine, then positive sine, then positive cosine, then negative sine, negative cosine, right? We're going to keep going through this 1, 0, negative 1, 0, 1, 0, negative 1, 0, and so on and so on and so on, right? In other words, this pattern appears to continue, right? Which suggests that there's an infinite polynomial, right? I'll just continue the pattern. Right, we're skipping all the even terms. Those turn out to be zeros as coefficients. And then we get each power over a factorial of that power, and we're alternating positive and negative, right? So I think you probably see what's going on here. Let's try to write that as an expression, right? Because one thing I want to do here is test this series for convergence, right? Where is this actually good? When we glanced at the graph a minute ago, it seemed like it was getting to be pretty wide where it still looked like a good approximation. So what I want to be able to do is write this out as some kind of, in summation form, okay? Well, there's one thing that I can see is happening pretty clearly. Negative 1 is going to be alternating. I'm going to leave, well, I'll put n there for now. We may or may not need to subtract 1 from that or add 1, whichever way you want to go. We have some decisions to make. This is a little bit different than a lot of the series we've written out. You might notice that we don't have something I can write that says B0 for every even and then do something else for all the odd ends, right? That's what happened here. The coefficient was 0 for all the evens and then 1 over n factorial for all the odds. I don't have a thing I can write that means that. But we have a little trick for accomplishing that, which is we skip over the even powers. So I'm going to write this and then we'll talk about it. And I'm going to start. Okay. So what have I done? First of all, I'm starting at n equals 1, right? Well, why? Because I've written this expression 2n minus 1. This is a nice way to skip all the even powers. This, for every value of n, this is going to give you an odd number, right? So if I started at 0, I would have 2 times 0 minus 1, and this would that's not what we want, right? We want to start at the power of 1. So by starting at 1, I get the right thing here. 2 times n minus 1 gives me a power of 1 and a 1 factorial in the denominator. N minus 1 means when I put in 1, this is to the power of 0, so this becomes a positive 1. That first one's positive. When I go to n equals 2, I want it to be negative. I get 2 minus 1, so a 1. Negative 1 to the 1 is negative 1. There's my negative. When I put 2 in for n here, 2 times 2 is 4, minus 1 is 3. I get 3 in the denominator with the factorial. And this goes on and on and on. This is a way to get it to skip all the even powers, okay? So this is a nice trick that we can use. I'm gonna let you guys do cosine on your own, and you're gonna need to use a similar trick except skipping all the odd powers. So I'll let you think through that one, but this is a nice trick to know. And you'll see that this is exactly this series if you write it out. And it's just what emerged from our work to do the 5th degree polynomial. The pattern was pretty apparent, and this is what shows up. Let's now test the interval of convergence using the ratio test. All right. So again, when I take the interval of the ratio test, I'm going to ignore the -1 part since the absolute value takes care of that anyway. So I'm looking at this piece. I'm going to have the n plus 1th term. So that's going to look like x to the 2 n plus 1 minus 1 over 2 n plus 1 minus 1 factorial. And I'll just take the reciprocal of the nth term. So that'll look like 2n minus 1 factorial over x to the 2n minus 1. All of this is in absolute value. We do our algebra. So what happens? Well, let's just go ahead. 2n plus 1 minus 1 is going to be 2n plus 2 minus 1. So that's going to look like x to the 2n plus 1, right? 2 plus 2 minus 1 gives me the plus 1. Same thing. I'm gonna move things around, put all the x's together. So I've got 2n minus 1. And then here, I've got 2n minus 1 factorial over 2n plus 1 minus 1. The same thing that we got there is going to be 2n plus 1 factorial. All right, let's see what we get. 2n plus 1 is 2 exponents bigger than 2n minus 1, right? If you add 1 to this, you get 2n. If you add 1 again, you get 2n plus 1. So, or you can just use subtraction. 2n plus 1 minus 2n minus 1 leaves me 2 factors of x. So I've got an x squared from these. 2n minus 1 factorial over 2n plus 1 factorial. Well, remember what these are. This is an integer 1 bigger than 2n. And then the product of every integer below that, goes up as far as an integer below 2n, right? What that means is they've got all the same factors, except this one has a factor of 2n and 2n plus 1 that the top didn't have. So everything cancels besides these two factors, right? I also dropped the absolute value. Our n's are positive, so the denominator is positive. X squared is positive, so I don't need the absolute value anymore. And this is what our ratio looks like. Let's take the limit as n goes to infinity of x squared over 2n plus 1. X is a constant as far as n cares. So it's x squared times the limit as n goes to infinity of 1 over 2n plus 1. We've got a rational function in some sense with degree 0 in the numerator and degree 2 in the denominator. This is growing much faster. This one's not growing at all. This limit is 0. The limit is 0. Right? So regardless of the value of x, the limit is 0, which means, according to the ratio test, this series converges for all values of x. In other words, the radius of convergence is infinite, or this is for x between negative infinity and infinity, right? So we've got a series here that is good for all values of x, okay? Which it is, in fact. And this is the expression for sine, right? These two are equivalent, right? I've just written it out more explicitly here, but here's a nice expression for the sine function as an infinite series, okay? You'll see, well, let me point something out. Notice sine is an odd function, and we notice this is an odd polynomial, right? We're only getting the odd terms, which should make some kind of sense. We don't want to have even terms in there if we're going to end up with an odd function. I'll let you see what happens when you work out the cosine function on your own. There's some nice relationships between the two of them, but I'll leave that for now. Let's do one last thing, though. Let's just glance back at the graph, which we had started to look at. I'll zoom out just a little bit more, right, and continue to add terms. This will take a moment for the computer to catch up. It's hard to know when it's gotten there, but as I'm adding them, you see that we're laying down more and more along this sine curve, right? We've got this strange polynomial, right, with all these characteristic up and downs that polynomials have, but now they're nearly perfectly lying along the sine graph, right? It's pretty amazing. All right, I'll stop that one here. I'll see you for the next one.